Thank you for attending Glass Options for a Healthy Built Environment. My name is Kayla Natividad, and I'm an Architectural Technical Services Engineer with Pilkington, North America. I'm going to be guiding you through this presentation today. Credits earned upon completion of this course will be reported to AIA for all AIA members. Certificates of completion can be available upon request. This presentation is protected by U.S. and international copyright laws. Reproduction, distribution, display, and use of the presentation without written permission of the speaker is prohibited. During this course, we'll be discussing the impacts of material selection and the design has on the built environment. We'll also discuss some of the benefits of coated glass products and glass options that will help maintain and optimize the building occupant experience. Upon completion of this course, everyone attending should be able to describe material and human consideration in material selection, explain the difference between antibacterial and antiviral technologies, understand how photocatalytic reaction can inactivate bacteria and viruses, and also explain how VOCs can impact indoor air quality and describe some methods to mitigate it. So to address all these learning objectives, what we're going to do is break this into three parts. The first part will define the built environment and describe its role in human health throughout history. In the second, we'll discuss material considerations and learn about antimicrobial glass technologies available today in the third. So let's start by defining what the built environment is and how it can impact human health. The U.S. Environmental Protection Agency defines a built environment as the man-made or modified structures that provide people with living, working, and recreational spaces. This means the built environment is a major component in everything that affects all parts of our lives. So from the buildings we live and work in to the transportation systems we're using to go from place to place. Essentially, everything we come in contact with on a daily basis can be defined as the built environment. The built environment significantly affects a public's health, and it has throughout history, really. We'll go through some of these series, but really through exposure to toxins, pollutants, pathogens, or prevention of exposure, the design of physical spaces has really been linked to the severity or not severity of the spread of chronic and infectious disease throughout history. So let's take a step back and look at how the built environments really affected human health throughout history. And we'll start at the 19th century. So now we're talking the Industrial Revolution. Hundreds of thousands of people are flocking to new cities. There's no real air or water quality monitoring. Urban planning doesn't exist. So people live where they work, where they do other things. And what really happened is a lot of these cities tended to be overcrowded, very unsanitary, and it resulted in an increase in disease and epidemics, and in turn, a decrease in life expectancy. So it was during this time that the connection between the built environment and human health was really highlighted, because this was the first time that this many people were congregating into these smaller spaces. And so it was really where we started to see the need for the use of urban planning and really organizing where things were going to go and how it would be set up. So through the development of sewer systems, the movement of residential areas away from industrial facilities, and the inclusion of light and fresh air in building design, life expectancy really started to rise. But as we know, Rome wasn't built in a night. And so we start seeing these positive changes, but as we move into the 20th century, we're still seeing significant overcrowding. There's poor sanitation, really low hygiene standards overall in a lot of communities. And so we really have to take that into consideration when we look at how pandemics and things have spread throughout history. So, for example, let's consider the built environment's effect on the Spanish flu, which I'm sure we've all heard about recently, or more about recently, that lasted from 1918 to 1920. And so the Spanish flu is known as one of the deadliest pandemics in history. And while there's obviously a number of differences between the current COVID pandemic and the Spanish flu, I'd like to highlight how some of these differences in the health system and the infrastructure of the built environment impacted the severity of the pandemic. So at the time, the Spanish flu hit the world before antibiotics were even invented. And a lot of deaths, perhaps most, were not caused by the flu itself, but by secondary bacterial infections. And these secondary bacterial infections generally could be related to poorly regulated built environment. And so um, we keep moving forward in history. We see antibiotics, um, the invention of antibiotics and introduction into the population. So now there's a decrease in the spread of infectious disease. By the mid 20th century, the connection between human health and the built environment didn't seem as apparent as it did in previous years. Infectious disease had really been brought under control, and as a result, the layout and the planning of cities came to be viewed as more of a matter of aesthetics or economics rather than for health. They weren't moving people away from these industrious, toxic places anymore. Now they were just more organizing cities to, be more aesthetically pleasing. Um, so over time, infectious disease threats became less prevalent and focus shifted to the prevention of chronic diseases. And you see the shift occurring really through a focus on human behaviors and regulations on toxic substances included in building products. So we still see this now, right? We see smoking restrictions. You can't smoke indoors. You can't smoke within a certain proximity of building entrances. We see laws banning production with toxic substances like lead and asbestos that are still in place today. So we're moving more towards a lot of these chronic diseases. And essentially until early 2020 and the introduction of the current pandemic, the primary public health problems were chronic disease rather than infectious disease. So we have a lot of people thinking of ways, how to design buildings and infrastructure to reduce chronic illnesses, that have been associated with poor air quality, water quality, poor lighting conditions or thermal comfort. Now we're seeing more studies that are showing chronic diseases linked to poor sound control and essentially noise pollution. And due to material toxins, we're still seeing a lot more push toward that direction in terms of material transparency, requiring environmental product declarations or life cycle assessments of products. And so now, a lot of voluntary building standards are aimed at improving energy performance and environmental or human impact. So you have LEED, Living Building Challenge, WELL, Passive House, and they're all being widely adopted as cities move towards reducing their environmental impacts. But by reducing their environmental impacts, they're in turn improving the quality of life for the general population. So since essentially March 2020, post-COVID pandemic introduction, we're still focused on all of these high performance buildings and reducing these chronic diseases because we know they're there and we know this is a problem that we need to tackle. But we also have a newfound concern of preventing and mitigating the spread of infectious disease. So rather than going through all of these different reasons that can cause chronic illness or these different causes, I'm really going to focus on air quality and material selection, as well as infectious disease, and how we can go through and help mitigate these through our design considerations. So this brings us to section 2 on our material design considerations and human. Studies have shown that humans spend approximately 90% of their time indoors, and so since the majority of our lives are spent in direct contact with the built environment, I think it's really important to take this into consideration in all of our designs, right? Some ways we can help optimize comfort in our designs is just by consciously selecting our materials and acknowledging the way that occupants interact with the space, and what that could mean for not only themselves but future occupants of the building. So we'll start by just, talking about indoor air quality in general, and then we'll get into a little more specifics. Um, so concentration of air pollutants are often 2 to 5 times higher indoors than typical outdoor concentrations. And this can be linked to numerous sources, but really there's two major building trends that have had significant impact on the increase in indoor pollutants across recent years. And so the first building trend that we see is the focus on high performance building designs. I mentioned in the previous slide that now we're seeing these really high performance designs through LEED and WELL and Passive House. But essentially what a lot of this is calling for, especially Passive House, is the use of increased air tightness in envelopes. And like, for example, um, you want to improve your air tightness of your structure to reduce heat loss, prevent moisture infiltration. And a lot of times in these airtight designs, it's really important to maintain proper ventilation because that's kind of an afterthought um, of, post sealing the facade. And so by maintaining proper ventilation, you can help reduce the concentration of indoor pollutants and allow for that air exchange to occur. The second building trend that we see that has really driven or caused a rise in indoor concentration of pollutants is the use of synthetic building materials. So synthetic materials can contain volatile organic compounds, or VOCs, that are gradually emitted throughout the life of the material. And these VOCs can affect air quality and can impact human health and comfort through a couple different ways. So some of them may just be odor, or they may cause what we call sick building syndrome. You're getting irritation, whether it's your eyes, your sinuses, whatever, and essentially lead to like chronic toxicity. And so what we really want to do is focus on, if you want to improve your indoor air quality, and part of the way you would do that is by focusing on lowering your VOCs in your building. And so the lower the VOC of a material, the less concern it is for long-term impact on human health. So whenever we're thinking about improving air quality, it's also we have to take into consideration our material transparency and what our actual materials are doing, whether they're having a negative or positive impact on your air quality in your space. And so some ways to go through and improve air quality, as we discussed, are, you have conscious material selection, but also proper building ventilation can really help prevent sick building syndrome. In some cases, if you're doing a, if you're going through and using an existing building, you don't have as many options in what you can do. So that's when conscious material selection is really important. And so another thing I'd like to know, as you know, this presentation is about glass options. USGBC, who created LEED, recognizes glass as an inherently non-emitting product. And so even if glass is used as your interior partitions or things like that, it's essentially has no impact on introducing VOCs into your space. Actually, what we'll be discussing a bit later is some coated glass products have the potential to have a net positive impact on indoor air quality. So not only are they not introducing these new toxins into into your indoor space, but they're actually potentially negating and helping reduce some of those pollutants in your space. So now I want to just kind of shift my stance a bit, and now we want to talk about more human interaction and the spread of infectious disease and what we're seeing day to day right now whenever we go anywhere. And so I want to just hit a few buzzwords really quick, more so we can make the clarification now and we can discuss a bit more later. Um, so the first one is pathogens. If I talk about the spread of pathogens, really a pathogen is just a microbe that can cause a disease. And so pathogens could be bacteria, they could be viruses, they could be fungi. It's really just more the overarching, the general title of it, and bacteria and viruses are subcategories. I'd like to note that I am not a medical professional by any means, but this is just something as we've gone through and we've done a lot of research into these topics. These were some of the more important things that we found that we would like to understand. And so part of the reason I want to make that clarification is because a lot of times we see things marked as antibacterial, antiviral, antimicrobial, and what, we want to know what that really means and how is what we install going to be effective against what we're trying to be effective against. And so antibacterial, as it states, is effective against bacteria. Antiviral, if something's marketed as that, is proven to be effective against viruses. But if something's marketed as antimicrobial, it's just effective against microbes in general, right? So it could be bacteria, or it could be viruses, or it could be fungi, and it isn't necessarily calling out a specific thing. And so that's something you want to know whenever you're going through and selecting some of these antimicrobial devices or building products that you may be using, is that you want to go through and see what these are categorized as, because then that'll show you what they're effective against. So moving forward with that, there's a couple things we need to understand, and one of them is, okay, well, now we know about these infectious diseases, but how are they transmitted? Well, there's really three major topics or three major ways how they're transmitted. One is through direct contact. You're shaking hands with somebody, you give somebody a hug, person to person, there you go. The next is through droplet spread. So as we're talking, we could be further away from each other, but as we've all kind of experienced at some point or another, you do have droplets coming out of your mouth as or when you sneeze or something, and on all of those particles, that's where you'll get some of your spread. And the other is through indirect transmission. So whether it's airborne, as you're talking, it spreads out, it lands on the particles in the air, and it stays in the room for quite a while after. Or what I want to focus on is vehicle or fomite transmission, and that's where you touch an inanimate object and you potentially transmit these microbes onto the inanimate object. So the next person that comes in, when they touch it, they end up picking it up. And so as we're going through and we're seeing a lot of these companies and restaurants and just buildings adapt to post-pandemic or really pandemic life, we're starting to see a lot of these, like, barriers come up between the cashier and the person buying whatever they're buying. And so, that's used to help prevent the spread of droplet spread. Or you're starting to see a lot more people wiping down. You see tons of people creating hand sanitizers, and that's really one, to help prevent direct contact, because if you are sanitize your own hands, you don't have that spread, but also to help prevent vehicle or fomite transmission, constant wiping down of surfaces and things like that. And so there's a couple different ways that through our material and design selection, we can help prevent these. And that's why I've highlighted droplet spread and vehicle, because we can't really control, as architects or designers or engineers, we can't control if people are hugging in the space, but we can help prevent some of the interactions that we know are going to be occurring, such as the barriers between the cashier and the customer. And what we can also try to help prevent is vehicle transmission through the use of antimicrobials in our building products that we know might be high touch surfaces, or that we know is likely to come in contact with some of these things. And so general methods for microbial abatement are obviously wash your hands, avoid contact with people, cover your coughs and sneezes. And again, we don't really have control over these things, but one thing we as a product manufacturer can help contribute to, and also you as designers or engineers who are going through and fixing these spaces, is helping with how often the surfaces are cleaned and disinfected, because there are products that are essentially continuously cleaning and disinfecting that we can use. And so that's really where I'm going to be focusing now on what are some of these products and antimicrobial products that are available today, and how do they work, and where are they generally used. So there are a number of building design situations where very specific needs arise for glass, and we've really responded by testing and developing glass products to meet those applications. I'm going to go through and introduce a couple glass coating technologies that might reduce the risk of surface transmission of bacteria and viruses. So in this section, we're going to review 3 different glass technologies. The first is electrically conductive or heated glass. The second is silver and copper coatings. And the third is the use of photocatalytic coatings, specifically titanium dioxide-based coatings for antimicrobial properties. So let's start with our conductive coatings used for heated surface. Whenever we think of anything potentially being infected, or you think of your contaminated water, you think of a lot of things. It's boil it, kill it with fire, just make it really hot and it'll kill anything that's on the surface, right? Well, heat's generally been used as a method to achieve sterilization and disinfection throughout history, and we see that it's effective, and we have products that have conductive coatings that will allow for the glass surface to be heated, which is essentially effective through dry heat sterilization. So what you see is whenever your bacteria viruses land on the surface of the glass, you have dry heat sterilization through conduction. So as your glass surface is heated, the heat is absorbed by the glass and is passed along to the bacteria and viruses on the surface of the glass. And essentially what happens is the heat, it destroys these microbes through the denaturation of proteins. And so it causes these to break down and essentially be inactivate them, so they're no longer harmful to the building occupants. We see conductive coatings more often. We're familiar with them in refrigeration units, but that's more just because that's where they've always been used to prevent condensation. There are products available that are aimed for disinfection and sterilization of the glass surface. So this is just an example of how effective it is. So you'll see along here as you go through and you start increasing your glass temperature. So this is your 4 degrees Celsius, this is your 70. You see that the stability of COVID-19, SARS-CoV-2, actually significantly decreases once you start hitting certain temperatures. So if you're at 4 degrees, it can last on the surface up to 14 days approximately. But once you raise to a certain level, you really significantly reduce that up to, could essentially sanitize the glass surface within 5 minutes, 30 minutes, significantly less time. And so here's just a couple additional information for you on that. But really where we're getting with is if you use conductive coatings, it's possible to heat the glass enough that you could take advantage of the high temperatures, neutralize the bacteria and viruses, and essentially help reduce the need for continuous, or having somebody continuously go around and have to disinfect the surface themselves. It just reduces some of that manpower. It's not a Doesn't mean you never have to clean the glass, but it at least means that you have a longer time between cleanings that you can use. Now we'll go into silver and copper coatings. This is something that we're starting to see a lot more of recently. Silver and copper have always been known to have natural antimicrobial properties. But one thing to note is that a lot of these products, that if you're buying them, they have to be registered through the EPA. And there's a couple different ways that they can be registered, but silver and copper coated products are classified as pesticides by the EPA, and the reason for this is because the silver and copper coating itself is killing the microbes that come in contact with the surface, and so it doesn't need any outside factors to help optimize this killing or activate the killing activity of it. It just naturally has these antimicrobial properties. So the way this works, though, is there's trace amounts of, or you have your silver copper coating on the surface of the glass, and as your bacteria lands on the surface of the glass, trace amounts of the bacteria, of the bactericidal silver or copper ions will leach from the surface and essentially enter the bacteria and kill it through ionization. So what they do is they attach themselves to the bacteria, they disrupt cell walls, and they eventually burst the membranes of the bacteria, deeming it harmless. In the same way that it leaches onto the bacteria when it touches the surface, as the building occupants go up and come in contact with this glass or with these coatings, the silver and copper will also leach to the skin of the building occupant. So every time you touch it, there is nanoparticles gradually coming off of the surface of the glass. A lot of times with silver and copper coatings, they are marketed to eliminate stain and odor causing bacteria. And you see these used more in not large scale applications like entire facades, but more as interior applications. You see them a lot in healthcare. You'll see them on touch screens where you know that there's a lot of people coming in contact with these. But they tend to be in somewhat smaller designs. And the last I want to focus on is the use of photocatalytic coatings or titanium dioxide based coatings. Um, in this case, whenever you go through and you register this product, it's actually classified as a pesticide device by the EPA. And part of the reason is because the titanium dioxide coating itself isn't what's killing or deactivating the bacteria and viruses. What actually is occurring is it's the combination of a UV light, the titanium dioxide coating, and general airborne moisture. So really just the natural moisture that's already in the room. And what these do is when you have this combination, they create these reactive oxygen species on the surface of the glass, these essentially hydroxide and oxygen molecules. And in that case, whenever bacteria and viruses land on the surface of the glass, the ROS inactivate the microbes on the surface of the glass through the degradation of the cell wall and essentially disrupting the RNA. So fairly similar to what you're seeing in your silver and copper coatings, but you need that combination of a UV source, the titanium dioxide coating, and your natural airborne moisture. And essentially what happens is these viruses and bacteria are deactivated, they're broken down, and eventually turned into water vapor and carbon dioxide byproducts. So A little bit more on these photocatalytic coatings. So photocatalytic coatings have these antimicrobial properties, but they've also been proven to have positive impacts on indoor air quality, as we mentioned earlier. So um, there are studies that go through and show that by the use of titanium dioxide coatings, air quality improvements can occur through the reduction of VOCs, ozone, and NOx, and this in turn will provide a net positive impact to your indoor air quality when applied to the interior surface of your facade or your glazing. In these cases, you have the natural UV occurring from the sun, so you don't need a artificial UV source, but you are able to just have this continuous, we'll call it like a purifier almost, right? Just this continuous effect on that's occurring on the surface of your glass. So a quick example of um, what I mean by this and how effective could it potentially be? Well, we've done studies that show there's a NOx reduction performance in your air quality. And so what happens is when this NOx comes in contact with the surface of the glass or with your coated surface, the NOx is converted to harmless nitrates. And this can occur at an abatement rate of approximately 277.5 micrograms per meter squared hour. So essentially, here's a quick little equation. I try not to bring math into my presentations very often, but it happens sometimes. And so if you go through and you know approximately how much NOx you have in your space, what your glass surface is, you can go through and say, okay, well, if we have a glass surface of this area, multiply it by your abatement rate, and you'll know how much NOx you're reducing within an hour. Multiply it by however many hours, and that's how many you'll reduce within a work day or within the entire day or within the lifetime of the glass. So whenever we look at our photocatalytic coatings, we're really aiming to use it as an interior glass surface because it can be very large scale and it's a pyrolytic coating, so it's very durable, can be bent, can be a process the same as essentially most uncoated glass products. And so really for these kind of situations where there are people coming in contact with this interior surface of the glass. And through photocatalytic deactivation, you see that it can, in the same way that silver and copper did, it can eliminate stain and odor causing bacteria. Also has been proven effective against envelope viruses, including SARS-CoV-2 or COVID-19 surrogates. It's shown improvement in air quality and really just more focused on the use of in highly populated areas where you might have some of these concerns. So lobbies, dining halls, mass transit, interior of buses or bus shelters, things like that. So really taking a step back from this overall presentation and looking at where we are, there's a couple key takeaways that we can have from this. And really the first one is we know that the built environment significantly affects human health. And there are things we can do to help mitigate this. And so through conscious material selection, proper building ventilation, and just general design, we can help prevent, sick building syndrome in terms of air quality, but also try to help prevent the spread of infectious diseases through these contact with high touch surfaces or building products. And we also have gone through and looked at a couple different existing glazing materials that can contribute to disinfection strategies and reduce the risk of surface contamination. I want to make it really clear that by using these materials, you're not necessarily saying you don't have to clean them anymore, but it at least helps with put some peace of mind into building occupants knowing that there is something actively working 24/7 to help, and two, just to go through and have a somewhat reduction on, potential like building staff that has to go through and do this. It just helps throughout the day on this, really. So if you have any questions, these are some of the references that we used, and feel free to contact myself or your sales rep for your region, and we'd be happy to answer any questions for you, or give you or send out any samples or product literature. So just let us know. Thank you for your time.